So as I've tried to indicate to you guys, there's a set of rules, and if you apply the set of rules, you should be able to come up with information about how a situation or a system will behave. But there are rules, and those rules are inflexible. So this system will only rotate if there's an unbalanced torque acting on it. Each of those two masses will only accelerate if there's an unbalanced unbalanced force acting on them. Now, with that statement being thrown out there, it's not necessarily easy to figure out how this system will behave. In order to analyze it, you'd probably need to do the same things we've been doing, which is apply net force to each of the boxes, or each of the masses, and net torque to the pulley. Herein lies one of the problems, though. In doing that work, if you do it without careful thought to the details, you'll make silly mistakes. Grading your quizzes yesterday, I found lots of silly mistakes. They crushed you in the end because you made so many of them sometimes. But some of the mistakes were bad algebra, canceling out things you can't cancel out. You wanted the R to cancel out yesterday. You were desperate for it. Do you guys know what I'm talking about? It didn't. And when it didn't, you were stuck because you wanted it to be exactly the same as the one before. Well, that's not the way this works. You work the algebra as it's presented to you. Now, you can get a net torque problem and a net force problem. I know you guys can do those things. You can probably recognize that in this problem, the tension here, we'll say tension on the right, is different than the tension on the left. Right? We've kind of discussed that possibility. It's a massive pendulum, and it has inertia, and so those two tensions wouldn't be the same. But still, whether or not this accelerates is still going to be based on net force, and whether or not this accelerates is still going to be based on net force. But you're going to reach a point in the problem where you're going to have to make some decisions about those functions, because those functions are going to have things like acceleration in them and mass in them. And the only way those functions can cooperate together is if you have the same variables appearing in those equations. That's what we've been doing, right? Trying to develop a set of equations that have the same variables that represent the same unknowns so that we can do an algebra solution to them. Does this box accelerate the same as this box? Meaning if this is spinning this way, will this one go up the same amount that this one will go down? I'm not making this hard. You do understand that this one is attached to this portion of the disk, and this one is attached to the bigger portion of the disk. So if this one turns a little bit clockwise, this one will go up more than this one will go down. Everybody understand that? So this has to be acceleration on the right, this has to be acceleration on the left, and they are not the same. That's the first mistake I'm sure you made, or were making. However, this is one pulley. If the inner pulley makes one revolution, how many revolutions does the outer pulley make? One. This object has only one acceleration. Now, we know how these two linear accelerations are related. We know AR has to equal alpha times R. And AL has to equal alpha times 2R, because the outer radius is twice the inner radius. This problem is the same as the other pulley problems, except now, instead of getting a single expression for A, you should do the problem in terms of alpha. Yeah, you're going to have some R's in your answer. Fine, R's allowed in the answer. So instead of converting all of it to A, convert all of it to alpha, because alpha is the same for all of them. That's how you do this problem. That's not a trick. Did I tell you? You need to consider the way in which the system moves. That's considering the way in which the system moves. You want a situation in which the motion of the system was different. This is the way the motion of the system is different. It's an interesting question. You should do it. It's fun. There's some of these that aren't fun. This one's okay. Because once you know that, this one falls together pretty easily. And you can find the individual accelerations. One's just twice the other. So that part's no big deal. Okay, fun times. Do you recognize this thing? Not the thing from the lab. Do you recognize what this represents out in the public world, in the wild? Have you been to Gwazi and you seen that little kid ride where all the kids are in a circle going around in their little swings? They had an adult version of that at Busch Gardens that was much bigger, and it lifted everybody up a solid 30 feet first and then started spinning them, and you were way up in the air. You understand that you can't have that cable fail, right? That the study of this is the study of how you build that. Now, you might not be building that, but some of you went to the state fair probably. This ride is there, isn't it? In many forms. And some guy with like a few teeth and 3 fingers took your ticket and you trusted him to put that thing together. I assume you were hoping that it was inspected and maybe hoping that the guy who designed it knew what they were doing. Or you just assumed that everything would be just fine. You do understand that that's not the takeaway, right? So here's why this problem is both, I think, a successful application of first semester physics, but also a nightmare at the same time. You are supposed to be finding I as a function of the speed. And let's just talk about this thing for just a moment. Yeah, we're going to add some other stuff to it, but this is a point mass. We've had that discussion already, right? Is there anybody in the room who doesn't remember that as you spin this thing faster, this angle is going to increase? Right, we did this first semester. You spun something above your head. Many of you unsuccessfully, but you recognize that that angle gets greater the faster it spins. We never found a direct relationship with this, but we kind of did if you think about the force part of this problem. The force part of this problem is a reminder that there is a force of tension acting in one direction and a force of gravity acting in another. The tension serves 2 different purposes. One purpose is to keep the object from falling to the ground. It provides a component that is upwards to balance the weight. The other portion is the part that is towards the center, that serves the purpose of providing a centripetal acceleration because the object's moving in a circle, right? We did this problem. And when doing this problem, we remind ourselves that this is theta. We took this, force, moved him up there, straightened him out some so he looks like he's perpendicular. And we said, well, Tx is equal to T sine theta, and Ty is equal to T cosine theta. And then we said T cosine theta equals mg because the net force in the y direction is 0. And T sine theta is equal to MAC. Why? Because it's the centripetal acceleration for the object traveling in a circular path. Any of this ringing a bell? So it wouldn't be a stretch to go, okay, T sine theta equals m omega squared r. Or in this case, capital R, where that capital R is this distance. Actually, I guess I use capital R there. So we'll make it lowercase r, just to please me. Now, bringing this over and having T cosine theta equals mg, I can divide both sides and get omega squared r equals g tangent theta. All good? Yeah, you think so until we start getting down to the nitty gritty. Here's some more nitty gritty. Actually, let's use the other side for this. R is this distance. This part of R is L over 2, but this portion of R is L over 2 sine theta. So R is L over 2 plus L over 2 sine theta. Wow, that means this is omega squared times L over 2 plus L over 2, sine theta equals G tangent theta. See, theta as a function of omega. You see it there, right? Not a very clean function, is it? In fact, I'd argue that that's a pretty ugly function. Terribly ugly, in fact. Worse, you gotta put it in here. Right? The truth is, this is probably outside your mathematical capabilities. This one's tough. For a lot of reasons, but this is it. This is the analysis that you should have to do. You won't believe this next statement, but energy makes this problem look like a breeze. 2 steps. Because if you think about the energy side of this object's moment of inertia is definitely changing as it spins. But it's lifting these boxes, which means the potential energy is increasing too. The energy calculation here is easier to do than the force calculation, but the force calculation is tough. It's tough stuff. The first question is asking you to figure out a relationship for the moment of inertia as a function of the speed. That means I equals mr squared, and there's 2 of those, plus the bar, plus the solid cylinder. This is the part that matters because that's this part. And to do that, you need to find a way to substitute omega in for theta. So you have to collect theta in this equation, solve for it, so that's in terms of omega, and put it in here for r. And then substitute it in here, square it. Maybe don't do that. Maybe point to all those things and say that's what you're supposed to do. You're here at school today. I'll let you off the hook. Yeah.
Can you say that again?
Sure.
Just the part, what I exactly
What you would have to do what I've asked is it's asking for you to find an expression for the moment of inertia of this new system as a function of the angular velocity. So I have the moment of inertia as a function of the radius. Okay, times 2, because there are 2 boxes, plus the bar. I know I don't have to write all this out, but if I don't, somebody's going to ask about it, say, well, don't you have to include this? Plus the cylinder. There, I've included all of those things. We care about this part, right? Well, theta depends on how fast it's spinning. So I need a relationship that brings together theta and omega. That's collecting theta in this function is not easy to do. because I've got it on this side multiplied by omega. And I've got it trapped inside two trig functions, and they're not the same trig function. At least if they were the same trig function, I could collect them together, but they're not. So getting and teasing out theta from here is hard to do, to get theta as a function of omega. Again, I don't know that you can do it. Just so we have an understanding, a lot of these I've modeled off the AP exam, but try to draw it out so you would see the series of steps, the things that are happening. So I can speak just to the answer C, but I know that in this room there are people who have no blinking clue as to what to do here, even though this problem is, again, just apply your set of rules. So at the start of this problem, the object is fully sliding. That's all that's happening right at the very beginning. So if we look right here, right, coefficient of friction is 0. It has an initial velocity, but is not rotating at all. It's experiencing forces. There's probably weight and normal force acting on it, but there's no friction, so there's no reason to change its motion at all. All cool? The moment we hit this line, that's t equals 0. And the moment we hit that line, the situation changes. So let's try and get both of those on the screen. So I want the line to be right there. There we go. Okay. Suddenly, and I say this because it actually happened instantaneously when it transitioned from no friction to friction, suddenly there was a frictional force acting on the system. And Allie, I'm not insulting your intelligence. I know you know these things. I'm really doing this for the room. Is that okay? That meant that there is a force this way acting on the object. There's also an implied direction that this is positive. I'm going to stick with that implied direction. Now, frictional forces don't come without normal forces, so there must be a normal force there too. And that normal force is the result of the weight and the surface. Don't know why that's happening. There we go. Okay. So, considering that friction is acting on the object, if this object were just a box, you've done this problem before, right? An object slides, hits a patch where there's friction. You could work that problem. You could figure out the acceleration. You could figure out how far it travels before coming to rest. You could do that problem because that problem is a straightforward net force equals ma problem. And in the x direction, the only force is friction, so that equals ma. Since the right is the positive direction, I do have to explicitly make my friction negative because it points in the left direction. And I kind of want my acceleration to be negative here because it indicates it's slowing the object down, right? Because it has a positive initial velocity. In fact, I'd go so far as to say that you could come up with a relationship for the velocity based on this, because you can do net force in the y direction to come up with what you need for friction. Right, all of these things are things you've already done, and I feel a little bit disappointed. Well, no, I'm not disappointed. I don't know that you couldn't have done this part. I feel a little bit cheap that I have to explain this. So maybe I don't have to explain this. But I do know that v as a function of t is going to equal at plus v naught. So if I wanted to get the velocity of this object, whatever it is, as a function of t, I just need an expression for the acceleration in terms that I've been given, things like mu and m and g. But this is not a block, because if it were a block, it would just slow down and stop. This is something that's circular, which means that force is acting here, but the object's center of mass is here. Therefore, there's going to be a chance it's going to want to turn because of that, right? This object has the capacity to have its inertia and its shape change the way in which it moves. It having this shape means that the location to where the forces are applied makes a difference. So I need to look at the net torque part of this problem, which is going to equal I alpha. When I look at that torque, the torque is caused because there is a torque arm from here to here, and there's a frictional force acting that is a distance r away from the possible pivot point, which is at the center. So I'm seeing a torque of RF, but I'm going to treat this as a positive torque because it's in the complementary direction of motion, right? It's going to roll it this way. I still have a way of coming up with an expression for omega that's based on a motion equation because this is a constant. If I can solve for acceleration and knowing that it started from rest, I can get an expression for how the angular velocity changes as a function of time. Now, all of that to say that I have two different functions. One that describes the linear speed of the object and one that describes the angular speed of the object. Well, this number is getting bigger and this number is getting smaller. Correct? Rolling begins when v equals omega times r. That's when rolling begins. At that moment, friction is no longer necessary to change the speed of the object because we will have matched, we have synced up, and this point would now stop moving with respect to the surface. That's when rolling occurs. So if I put these two expressions together, I could solve it for t. That time is how long it takes for this condition to occur. Remember, I have an expression for how the velocity is decreasing as a function of time. And I have an expression for how much the angular speed is increasing as a function of time. I can figure out the time it takes for those to come into sync. That's how you do C. Does that make sense to you?
I think I'm messing up my algebra. Like, I got all that, but when I try to solve for t, it's not working.
Really?
I think I don't know. I think I'm making
Let's,
something.
then I'll go one more step further. I don't really want to, but if you did all of that and you're not getting an answer, I'll go one more step. The frictional force is going to be mu mg, right? Cancel out the m's. So my acceleration is just going to be mu g. So I will get negative mu gt plus v naught on the left equals. That is this expression. My angular acceleration is just going to be RF over I. I'm not going to put in a particular moment of inertia. So that's it, RF over I times t. So I just got to solve that for t. So I don't have space for that here. So and I shouldn't do this much in front of you guys, but Allie asked, so I can be nice. There. I'm going to solve this for t, so now I should do this. F is still mu g, so let me plug in the mu g for that. Oh, I'm sorry. Stop for a minute. I'm jumping the gun here. Not much, but I'm not being consistent, and I want to be consistent. This is RF T, but I still have to multiply all of that by R. Okay? And F is still based on friction. Okay? So now let's go back over here. So F is still, come on. F is still mu mg. So I need to sub it in. So I have mu g plus R times mu mg all over I times R. Did I do that right? No. And you should have stopped me. Golly, Mr. Shelton. This is times R. So that makes that R squared. So now it's V naught equals, geez, mu G. Now I feel confidence. R squared mu mg over I times T. There we go. That's what I wanted. All right. Now that looks really messy, but that's because I left mine in terms of I. I told you to pick something, right? I said pick a disk or a solid sphere or whatever. The reason I didn't worry about that, and the reason why I'm okay going through this with you guys, is look here. Rearrange the top. In fact, now that I've rearranged the top, let's regroup the top. You understand I is going to have mr squared in it. I is just going to make that a number. So you see why I did that? Because then I could put in a disk, a sphere, a hollow sphere, whatever I want. So T looks really cumbersome, but it also tells me something that I hope you guys see. I just pulled out the mu g. If we look at this, I is going to be mr squared, or 1/2 mr squared, or 2/3 mr squared, or 2/5 mr squared. This is the biggest it can be. This is the smallest it can be. If I put the big one in there, this just becomes 1, right? So everything in the denominator becomes 2, right? If I put the small one in there, that becomes 5/2, not 1, because I'll put the 2/5 in the denominator. And I'll have 5/2 plus 1, which is going to be 7/2, right? And 7/2 is 3.5. So I went from 2 to 3. That's all in the denominator. If you don't understand why I'm saying this, is this one will take the longest to stop, because that number will be a 2. And this one will take less time to stop, because it'll be a 3.5 in the denominator. Does that make any sense to you? It should, because this is a ring. It has the most inertia. It should be the hardest to change. It should take longer. This one is a solid sphere. It's the easiest to rotate. It should take less time to do so. And let's check our units real quick. Meters per second is this unit. This is, mu has no units, but this is meters per second squared for G. The units here cancel out, so it looks like I'll be left with units of seconds. So I'm pretty confident that my math worked out okay.
I made a very silly mistake.
Well, I made 3 of them, right? It's catching your mistakes that's important. And like I said, if you had, this would have worked out easier if you just chosen a value for I and worked it through. But because I asked this other question about placing them in order, I thought it best work it for I. That's a teacher job, right? Leave it in a more generic sense so you could plug it in at the end so we could make the comparison. But if you had just put in MR squared, it would have been easier because the R's would have canceled out, the M's would have canceled out. You would have something easier to work with. To find D, just use a motion equation, right? Now you have T, you know how long it takes, and you have an acceleration. You can just pick any motion equation you want to find out how far it's traveled. I would probably pick one that has a 0 in it. That would probably be a good way to go, if there is one. If you can't find one that has a 0 in it, find one that has a known quantity that you already know in it. Those are probably the easiest ways to go. But you need anything that will get you to delta x, because you're looking for the distance it travels. But you have acceleration, and since it's linear, you're focused on just the linear parts.